You know, for most of human history, something as simple as a scratch from a rosebush or just scraping your knee, that could literally be a death sentence. Bacterial infections were just this unstoppable force, a truly terrifying problem for early medicine. But then came the historic solution, penicillin. It absolutely revolutionized modern healthcare, basically turning fatal infections into manageable inconveniences. So welcome to today's Explainer. We're going to unpack the fascinating clinical journey of penicillins. We'll look at exactly how they work, when they're used, and what clinicians actually need to watch out for.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll meet the penicillins. Then, we're breaking down walls. We'll follow that up with clinical indications, explore the catch, side effects, and then finally wrap up with nursing considerations.
So Section 1, meet the penicillins.
Now, while anti-infective is a pretty broad umbrella term covering everything from antivirals to antifungals, penicillins sit firmly at the foundation of the antibacterial subclass. I mean, they are the granddaddy of them all, really. They're the classic beta-lactam standard that served as the absolute blueprint for decades of pharmaceutical advancements. They are highly specialized tools designed for one primary target, destroying bacteria. But how exactly do they pull this off?
Let's move to Section 2 and see how this builds, breaking down walls. And this brilliantly illustrates what's going on at the microscopic level. When we look at the cellular anatomy of a bacterium, the absolutely most critical feature is its cell wall. See, human cells, we don't have cell walls, we just have cell membranes. Bacteria, on the other hand, well, they completely rely on these rigid outer walls to maintain their structure and survive the massive osmotic pressure of their environments. This structural difference, this unique armor, if you will, is the ultimate vulnerability that penicillins are engineered to exploit.
So the mechanism actually happens in three distinct, honestly devastating steps for the bacteria. Step 1, the penicillin drug binds directly to specific proteins on the bacterial cell wall. Step 2, once it's attached, it actively inhibits the synthesis of that wall. It basically stops the bacteria from being able to repair or build its armor. And then step 3, without that structural integrity, the bacteria just can't withstand the osmotic pressure from its environment. Water rushes in, and the bacteria is completely destroyed through a process called lysis. Imagine overfilling a water balloon until the rubber just gives out and it violently pops. That is exactly what penicillin does to a bacterial cell.
Which brings us to Section 3, clinical indications.
Now, not all bacteria are built the same, right? And therefore not all penicillins are the same. We differentiate bacterial coverage primarily between gram-positive and gram-negative bacteria. Gram-positive bacteria have these really thick, exposed cell walls, which makes them highly susceptible to early generations of penicillin, like penicillin G. But gram-negative bacteria, they have this extra outer membrane that acts like a shield, making them much, much harder to kill. Over time, pharmacologists had to develop newer generations of penicillins, like amoxicillin or these really strong beta-lactamase inhibitor combinations, specifically engineered to penetrate those tougher gram-negative defenses. Choosing the right generation is really all about matching the specific drug's spectrum of activity to the specific bacterial culprit. It's a critical step to ensure efficacy and, to prevent the promotion of resistant strains.
All right, Section 4, the catch, side effects. Now, what's really interesting about this is that every powerful solution comes with a cost. When we introduce a compound designed to destroy cells, even bacterial ones, the human body can definitely react unpredictably. The most common adverse reactions are actually often gastrointestinal. Penicillin just isn't selectively targeted enough to distinguish between the bad pathogen causing a severe infection and the good commensal flora in your gut. So as a result, the drug disrupts this delicate balance, leading to microbiome dysbiosis, which frequently manifests as nausea, diarrhea, and just general GI upset.
Beyond GI distress, though, there is a much more critical side effect we absolutely must monitor, and that's hypersensitivity. On one hand, a patient might experience a mild allergic reaction, presenting as a simple rash or hives, and while that's uncomfortable, it's generally manageable. However, this can rapidly escalate to severe anaphylaxis. This is a life-threatening emergency where the airway swells and blood pressure drops. Interestingly enough, up to 10% of the general population reports a penicillin allergy. Yet clinical evaluations show that over 90% of those individuals actually tolerate the drug perfectly fine. They either outgrew the sensitivity or maybe it was just misdiagnosed initially. Still, distinguishing between a mild intolerance and the rapid onset of true anaphylaxis is absolutely essential for patient safety.
Let's move to our final stop, Section 5, nursing considerations.
This is where the theory actually meets hands-on clinical care. Because beyond just watching out for rashes and managing side effects, there are very specific clinical protocols when administering penicillins. And that brings up a bit of a medical mystery for you. When a patient is on this medication, what must a clinician look for in a routine urine test? I promise it might not be what you immediately expect.
So the crucial point here is that the protocol is to test urine specimens for glucose and ketones. But why is this so important? Well, certain penicillins, especially when they're given in high doses, can actually interfere with traditional urine glucose tests, potentially causing false positive results. Furthermore, monitoring ketones and glucose helps ensure the patient's metabolic state remains stable while they're fighting off a severe infection. This is incredibly important for diabetic patients whose systems are already under tremendous stress. It's a brilliant reminder that, we aren't just treating a localized infection, we have to monitor the entire systemic balance of the patient.
Let's rapidly fire off the most critical takeaways for clinical practice. Number 1, monitor for hypersensitivity continuously, especially during that first dose, because anaphylaxis can strike fast. Number 2, check those urine specimens for glucose and ketones to ensure accurate metabolic tracking. And number 3, actually scratch that, this is probably the most common yet vital instruction given to any patient. Ensure full course completion. Even if the patient feels better after 3 days, stopping the drug early leaves the strongest, most resilient bacteria alive. This doesn't just cause a relapse for the patient, it directly contributes to antimicrobial resistance, which is arguably one of the most severe public health crises in modern medicine.
Which leaves us with this final thought. By stopping antibiotics early, or just overusing them in general, we're effectively training bacteria to build stronger, smarter cell walls. I mean, we've gone from penicillin G to these highly complex synthetic combinations just to keep popping that microscopic balloon. So as bacterial walls continue to evolve and develop resistance, how will the next generation of anti-infectives keep pace? Are we going to find a new vulnerability, or will the bacteria eventually outsmart our best tools? It's a massive challenge for the future of medicine and definitely a topic for a future explainer. Thank you so much for joining me on this clinical journey today, and keep asking those great questions.